Hello everyone, welcome to Aeronaut's GATE Aerospace, and this is Gautami. Today we'll be doing 2009 propulsion questions. As always, first we'll be dealing with analytics. So according to 2009 GATE Aerospace paper, there were 4 1 marks questions and 6 2 marks questions from propulsion. So totally there were 10 questions and 16 marks questions from 2009 paper, and out of that 6 questions were from jet propulsion, 2 questions were from rocket propulsion, one from AFC and one from thermodynamics. So when you look clearly into all these analytics, you get to know that jet propulsion and rocket propulsion has taken the maximum part. like uh, you can majorly focus on jet propulsion and rocket propulsion because the probability of you answering to the questions are more, and getting a right answer is more in jet propulsion and rocket propulsion. And yeah, so before we begin with the solution, so if you haven't subscribed to our channel, do subscribe and share it with your friends. This channel is completely dedicated for those people who want to study and clear GATE Aerospace, as well as who are very interested to learn aeromodeling. So let's begin. Question number 1. The propulsive efficiency of a turbojet engine moving at velocity u infinity and having exhaust velocity ue with respect to the engine is given by. Okay, so here they have mentioned about propulsive efficiency. So let us write propulsive efficiency, which is equals to thrust power divided by propulsive power. Okay, so thrust power can be written as thrust into Ci, or you can write it as U infinity, divided by propulsive power is half into mass flow rate of air into UE square minus U infinity square. Okay, so thrust can be written as mass flow rate of air into Cj minus Ci. So it is UE minus U infinity into U infinity divided by half into mass flow rate of air into, so this is like a square minus b square, which can be written as a plus b into a minus b. So you can write it as ue minus u infinity into ue plus u infinity. So ue minus u infinity get cancels, mass flow rate of air get cancels. So the remaining is 2 goes on the numerator, 2 into u infinity divided by ue plus u infinity. So this is the propulsive efficiency. So according to this, option D, 2u infinity divided by ue plus u infinity is the right answer. Second question. An aircraft is flying at Mach 2 where the ambient temperature around the aircraft is 250 Kelvin. If the specific heat ratio of the air is 1.4, the stagnation temperature on the surface of the aircraft is. Okay, they're asking for stagnation temperature and they have given an ambient temperature of 250 Kelvin and Mach 2 and gamma 1.4. So we know the relation T naught divided by TA is equals to 1 plus gamma minus 1 by 2 into m square. So gamma 1.4 minus 1 divided by 2 into 2 square is 4. This is T naught into TA. TA is 250. So when you calculate this, it will be 1.8 into 250, which is 450 Kelvin. So stagnation temperature is 450 Kelvin. Option B is the right answer. Question number 3. The division of feed air to the aircraft gas turbine combustor into primary and secondary streams serves which of the following purposes? And there are three options. So, option 1, a flammable mixture can be formed. Cooling of combustor liner and flame tube can be accomplished. Specific fuel consumption can be reduced. So, here the option P, a flammable mixture can be formed, is a true. And Q, cooling of the combustor liner, because the air which is passing through the bypass, so the hot air stream and the cold air streams, this helps us to reduce the it is help to cool the combustor liner and the flame tube, the cold air which is passing through the bypass. So the option Q is also correct. And the specific fuel consumption can be reduced, no. So the correct option is option C, P and Q. Question number 4. Thrust available from a turbojet engine increases as altitude increases up to the turbo pause and then decreases. It remains constant at all altitudes and decreases as altitude increases. So the thrust available, and this is a Mach number here with respect to altitude. So this is sea level. This is some 3000 and this is 11,000 meters. So the thrust available will keep on decreasing as the altitude increases. So correct option is option D. Thrust available will decrease as altitude increases. Question number 5. An ideal axial compressor is driven by an ideal turbine. And the total temperature ratio across that, so T04 divided by T03 is 0.667, and if the total temperature at the turbine inlet, so T03 is 1500 Kelvin, and the specific heat Cp is equals to 1 kilojoule per kg Kelvin. The power drawn by the compressor per unit mass flow rate. So power drawn per unit mass flow rate is nothing but work done by the compressor, and we know work done by the compressor equals to work done by the turbine, and this can be written as Cp into T03 minus T04, and we know T04 is equals to 0.667 into T03, that is 1500, will give us 1000 Kelvin. So Cp is 1 kilojoule, T03 is 1500 minus this is, so once you do this you will get it as 499.5 kilowatt per kg per second. So this can be approximated to 500 kilowatt per kg per second. So the correct answer is option D, 500 kilowatts per kg per second. Sixth question. The performance of a solid rocket motor is improved by replacing the old propellant with a new one. The new propellant gives a combustion temperature. Okay, so combustion temperature of a new propellant is 40% higher. It is 40% higher than the previous propellant. So let us consider this an old propellant, without appreciable change in molecular weight of the combustion products and other operating parameters. Okay, by approximately what percentage is the specific impulse of the new motor is higher than the specific impulse of a old motor. Okay, so here they're asking you the specific impulse change. So specific impulse is nothing but Cj by G, right? And Cj you can write it as 2Cp into Tc. So from here we can write specific impulse is directly proportional to under root Tc, so temperature. So to find the change in specific impulse, you can write it as, okay, so 40% greater, in the sense you can write that as 1.4 times of old propellant temperature. So new temperature minus old temperature divided by old temperature into 100. So if you do this, you will get specific impulse as 18.32 percentage. So which is nothing but option A, 18%. Okay, question number 7. A solid rocket motor has an end burning grain of cross sectional area. Okay, cross sectional area is 0.4 meter square. The density of the propellant, so propellant density they have given 1500 kg per meter cube, and has a linear regression rate. So linear regression rate 5 mm per second. Okay, if the specific impulse of the propulsion system is 200 seconds, the thrust produced by the motor is, okay, so what is the thrust produced by the motor? So they're asking in kilonewton. So be very cautious about the units. Okay, so now the first thing always you have to do is whatever they're asking, write a formula for that. So now in this case they're asking thrust. So for a thrust, you know the formula, mass flow rate of propellant into Cj. Okay, now look into the given data. So mass flow rate of propellant is not given directly, as well as Cj is not given directly, but they have given specific impulse, and you know specific impulse is equals to Cj by G. So from here you can get Cj. So that is Cj is equals to specific impulse into G. So what is specific impulse? It's given 200 seconds and G, you know, 9.81. So calculate this. 200 into 9.81, you'll get 1962 meter per second. So you got Cj. Now the remaining term is you need to get mass flow rate of propellant. So for mass flow rate, you know the formula rho AV. So where here rho is propellant density, cross sectional area, and velocity is nothing but regression rate. So mass flow rate of propellant is equals to density is 1500 kg per meter cube, and cross section is in meter square. Okay, into regression rate is in mm, so convert that to meter per second. So into 10 to the power minus 3. Okay, so now mass flow rate of propellant is equals to 3 kg per second. So if you calculate, you'll get 3 kg per second. So now you got both Cj and mass flow rate of propellant. So thrust will be mass flow rate of propellant into Cj, which is 3 into 1962. So thrust will be 5.8 kilo Newton. So 5.8 kilonewton. So the approximate answer will be option B, 6 kilonewton. Question number 8. An ideal ramjet is flying at an altitude 10 km with a velocity of 1 km per second. Okay, 1 km per second can be written as 1000 meter per second. Okay. The ambient pressure is given as 0.25 bar and the temperature is 225 Kelvin. The exhaust gases from the engine are optimally expanded and leave the nozzle at 900 Kelvin. So exit velocity is equals to 900 Kelvin. Okay, if the specific heat ratio gamma remains constant, the specific thrust developed by the engine is, so they're asking specific thrust. Okay, so the unit for specific thrust, and as I told before, be very careful about the units. Here they have given in Newton second per kg, or they can even ask you in terms of meter per second, because we know thrust is equals to mass flow rate of air into Cj minus Ci, where they're asking you specific thrust. So specific thrust when you divide thrust by mass flow rate, you will get specific thrust. So this has two units. One comes from this term, which is meter per second, or the second comes from here. Thrust, unit of thrust is Newton, mass flow rate is kg per second. So it is Newton second per kg. So be very careful about the units. Okay, now, for specific thrust, we need Cj minus Ci. So here they have given us Ci, initial velocity. You need to calculate Cj, and it is an ideal ramjet engine. So for an ideal ramjet engine, we know the inlet Mach number will be equal to exit Mach number, and Mach number can be written as velocity divided by speed of sound. Okay, now inlet velocity divided by speed of sound can be written as gamma r Ti. Here this can be written as gamma r Te, and in question they have mentioned gamma remains constant and r is already constant, so these two terms get cancels. So to calculate Ve, it is equals to Vi into Te divided by Ti. So this is 1000 meter per second, Te is 900, and Ti is 225 Kelvin. So if you do this, your exit velocity, you will get it as 2000 meter per second. So you got exit velocity. So now specific thrust is equals to Cj minus Ci. Cj is 2000, Ci is 1000. Therefore specific thrust is equals to 1000 Newton second per kg. Okay, so 1000, option A is the right answer. Question number 9. A combat aircraft engine is equipped with an afterburner followed by a variable area convergent nozzle. Okay, the nozzle is choked. They have mentioned nozzle is choked here. The exhaust gas temperature is 750 Kelvin when the afterburner is off. And the same exhaust gas temperature is 3000 Kelvin when it is on. That means when the afterburner is on. Okay, when the afterburner is turned on, the mass of fuel added in the afterburner is negligible. The mass flow rate remains constant, and the specific heat ratio remains constant. By what factor must the nozzle area be changed? Okay, nozzle area be changed. Okay, to calculate this, we know a great formula, a relation between your mass flow rate and area. So that is nothing but maximum mass flow rate divided by A star into under root T naught by P naught into R divided by gamma is equal to some constant. And in question they have mentioned R is constant, gamma is constant, and mass flow rate is constant, and P naught is also constant. So from this we know that A star is directly proportional to under root T naught. Therefore A star when the afterburner is on divided by A star when the afterburner is off is equals to T naught when it is on, T naught when the afterburner is off. So when it is on it's 3000, when it is off it's 750. So the ratio of this will be, so when you do this calculation you will get it as 2. So the answer for this question is option D, 2. So this is the factor. By what factor must the nozzle area be changed, right? So they are telling when the afterburner is on, by what factor your nozzle area should be changed? By 2 times when it was off. So the answer is option D, 2. Question number 10. So this is a linked questions. Air enters the combustor of a gas turbine engine at a total temperature of 500 Kelvin the airstream is split into two parts. Okay, like there's a mass flow rate of air coming in which gets split into two parts. So one is primary air and the second one is secondary air. So this is the secondary air. Primary and secondary streams. The primary stream reacts with the fuel supplied at a fuel flow ratio of 0.05. So here there is a fuel supply and the primary stream reacts with the fuel supply here. The resulting combustion products, so that is mass flow rate of propellant plus mass flow rate of fuel, which is this. The resulting combustion products are then mixed with the secondary airstream. So secondary airstream is here. So they both get mixed and the resultant will be mass flow rate of propellant, primary air, secondary air plus fuel. Okay, the fuel has a heating value of CV is 42 megajoule per kg, and the specific heat of air and the combustion products are taken as Cp is 1 kg per. Okay, so this is Q, heating value. Okay, so the question number 57, if the sensible enthalpy of the fuel is neglected, the temperature of combustion products from the reaction of primary airstream with the fuel is approximately. Okay, so they're asking when this primary airstream reacts with this fuel, what is the resultant temperature of the combustion chamber? Okay, so for that, see, whenever there is a question related to combustion chamber, keep one thing in mind. You have to always do enthalpy balance. You have to do enthalpy balance. So whatever the input is there and whatever you are adding should be equal to whatever the output you are getting. So here the input is mass flow rate of air. This is input enthalpy Cp into T01 plus you are adding fuel into Cv is equals to mass flow rate of what can be written, mass flow rate of air plus mass flow rate of fuel, which you are adding here, fuel into Cp into T02. So we know T01, the this numerical is to calculate T02. So what we can do, we know F. Actually here one mistake. This should be mass flow rate of fuel. Okay, now if you divide the equation by mass flow rate of air, you will get it as Cp into T01 plus fuel, mass flow rate of fuel divided by mass flow rate of air is nothing but F into Cv, and this will be 1 plus F Cp into T02. So T02 can be written as Cp into T01 plus F into Cv divided by 1 plus F into Cp. So T01 is 500, Cp is 1, T01 is 500 plus 0.05 into Cv is 42 into 10 to the power 3 divided by 1 plus 0.05 into Cp is 1. So when you do this, T02 will be 2600 Kelvin. So here option C, 2600 Kelvin is the right answer. So next, question number 58. The approximate ratio of mass flow rates, approximate ratio of mass flow rate of primary airstream to the secondary airstream required to achieve the turbine inlet temperature of 1550 Kelvin. Okay, so what should be this ratio to achieve T03 is equals to 1550 Kelvin. Okay, so let's solve that. So question number 58, we need to calculate ratio of primary airstream to the secondary airstream for T03 is equals to 1550 Kelvin. So as I told before, the enthalpy should be balanced. So the enthalpy which your inlet plus whatever you are adding, fuel enthalpy, should be equal to the output. So here you can write it as mass flow rate of propellant T02 into mass flow rate of propellant plus mass flow rate of fuel into Cp plus the secondary stream we have to consider here, enthalpy due to secondary stream, that is Cp into T04 into mass flow rate of secondary stream is equals to, the output is Cp into mass flow rate of primary stream, secondary stream, and fuel into T03. So this is like whatever we are adding, this will be the first enthalpy, then the second enthalpy, and the overall product whatever you are getting is the output. Okay, so now what we can do is, everywhere Cp is constant, so you can neglect Cp or just you can remove it, and we know mass flow rate of fuel to the mass flow rate of air is nothing but 0.05. Here air can be, you can write it as primary stream, so mass flow rate of fuel can be written as 0.05 times of primary air mass flow rate. So now wherever you have mass flow rate of fuel, replace it by this term. So T02 into mass flow rate of primary stream plus 0.05 times of mass flow rate of primary stream plus T04 into the secondary stream into, okay, Cp we are neglecting, you can write it as mass flow rate of primary stream plus secondary stream plus 0.05 times of primary stream into T03. So if you rearrange the terms here, you will get 1.05 times of and divided by mass flow rate of secondary stream, because we need to calculate that ratio. So 1.05 times of mass flow rate of primary stream to the secondary stream into T02 plus, here you can divide it, so T04 is equals to divided by secondary stream 1.05 plus, if you multiply, add 1 point this, you will get 1.05 times of mass flow of primary stream by secondary stream into T03 plus, if you will get T03 ms into T03 divided by ms, you will get only T03. So now substitute T02, and if you take common mass flow rate of propellant primary stream to the secondary stream, if you take common, then you will have 1.05 times of T02 minus 1.05 times of T03 is equals to T03 minus T04. Okay. So this is what we need to calculate into, I'll take 1.05 common. So T02 is what we have calculated before, 2600 minus T03 is 1550 Kelvin is equals to T03 is 1550 minus T04 is 500 Kelvin. So if you calculate this, the ratio of primary airstream to the secondary airstream, will get it around 0.96, so which is approximately equal to 1. So the ratio is 1:1. Therefore, for the question number 58, the option D is the right answer. Question number 11. A piston compresses of 1 kg of air inside a cylinder. So 1 kg of air, in the sense mass is 1 kg. The rate at which the piston does work on the air. So here work is done on the system. So if work is done on the system, it's considered to be negative. It is 3000 watt. At the same time, heat is being lost through the walls of the cylinder at a rate. So heat is lost at a rate of 847.5 watt. And okay, so heat is not added to the system, it is lost from the system, so it is negative. Okay, so now question number 59 is, after 10 seconds, so after 10 seconds, the change in specific internal energy of the system they want. So for that, first we'll convert the watt and heat transferred into joules. That is 3000 for 10 seconds, that is 30,000 joules, and this becomes 8475 joules. And we know from thermodynamics second law, dq is equals to du plus dw. So change in internal energy is equals to dq minus dw, and dq is minus 8475, and minus dw is 30,000. So if you do this, you will get change in internal energy as 21525 joules. So change in internal energy is 21525 joules. Option A is the right answer. Okay, now question number 60. Given that the specific heat of the air at constant pressure and volume are Cp and Cv is given, the corresponding change in the temperature of the air. Okay, so they want corresponding change in the temperature of the air, and we have the internal change in internal energy. So change in internal energy is nothing but mass into Cv, T2 minus T1. Okay, oh, 1 second. And D1, 21525, mass is 1 kg, and Cv is given 717.5, T2 minus T1. So T2 minus T1 is equals to 21525 divided by 17.5. So when you do this, you get T2 minus T1 as 30 Kelvin. So here option C, 30 Kelvin, is the right answer. Okay, so this is all for your 2009 propulsion questions. Hope you liked it. So leave your suggestions and comments in our comment section, and based on number of comments and whatever the topics you need to cover, we'll work on that, and we'll give more videos on that topics. And yeah, all the best for your preparation, and you can follow us on Instagram, as well as Telegram group link will be provided in the description. So join us through that links. Thank you.